Hi everyone, welcome back to the Technion's ECE Deep Learning course. I'm Tal, I'm the instructor in this course, and today in this tutorial we are going to continue our discussion on optimization. But first let's do a quick, super quick recap of the previous lesson. So let's jump in. And here I am. Okay. So previously, we started our discussion of how we are going to build deep neural networks by talking about optimization, which is a core basic block. And we talked about type of functions, convex, unimodality. And we also discussed optimality conditions, what conditions are required to define an optimum. We talked about a general idea of getting to this optimum, and we talked about doing this in in iterations. And we call this idea gradient descent, and we calculated the gradient and took steps towards the optimum. And we had some guarantees. Basically, when the function is convex, then we know we have some convergence guarantees, but otherwise we still apply gradient descent, but we don't have any guarantees, only that we will probably reach some local optimum. And we discussed that usually we cannot compute the gradient on the entire data due to the fact that the data is huge or that we have a lot of features. So for example, images, they have a lot of pixels, and many pixels it's equivalent to many features, and we can't calculate, or it's very hard to calculate the gradient over the entire features, over entire images. So basically we wanted to do this in batches, and we call this idea a stochastic gradient descent. And we talked about the properties of each type of algorithms, and we discussed that usually in deep learning what we will do is a mini batch gradient descent. So we outlined some general rules regarding mini batch gradient descent, especially the update speed and how it's related to other hyperparameters such as the learning rate and batch size. Okay. And the main topic of the previous lesson was the learning rate, and we talked about the challenges that are required to optimize this, to tune this hyperparameter, and we hopefully want to get the just right learning rate, and it can have a great impact on the convergence or divergence of our training. And then we discussed an example of linear regression, and we showed that the gradient is super dependent on the scale of the features. So we have to perform some normalization or standardization over our features before we input them to our model or before we apply gradient descent. And finally, we talked about since we are going to perform mini batch gradient descent, then we need to have some scheduling of the learning rate. So we gradually decrease the learning rate until we slowly converge or conveniently converge to the optimum. And we discussed several schedulers, and the most simple one was the step decay, which I encourage you to start with, and then try the more complex ones, such as the reduced learning rate on plateau, which is tailored for supervised learning. When we have some validation metric, we can reduce the learning rate once we see that there is a plateau on our metric. So, for example, if we measure the accuracy, then when the accuracy gets to a plateau, that means that it does not improve anymore. Then this is a good indicator that we should reduce our learning rate. And usually when we do this, we see a bump in our performance, which is good. And as we gradually decrease the learning rate, we should reach the optimum where the accuracy does not change anymore. Now we compared several schedulers, and we saw that while being very simplistic, the step decay is usually a good approach. So I encourage you all to start with that. Okay, so today in this tutorial, we are still going to talk about the learning rate, and we are going to talk about adaptive learning rate, and we begin our discussion with momentum, and then we will move on to the more sophisticated adaptive optimizers, which optimize the learning rate per parameter. So it's not a global update, but a local one. Okay, so before we get into the to the formulation, let's drive this discussion, let's motivate this discussion from a physical perspective. So let's say we have our loss function, which is illustrated right here, and we initialize our model, our particle, our parameters on this on top of this hill here. And when we initialize there, we want to gradually converge to the optimum, which is hopefully somewhere around here. Okay. Right. So we're going to calculate the gradient and go in this direction. Now, the physical perspective actually helps us understand a lot of stuff about the gradient descent algorithm. Now, while SGD or gradient descent is simple, as we just saw, it has many virtues, but speed is not one of them. Now, for a step size small enough, gradient descent makes a monotonic improvement at every iteration. We saw that, and it should converge to some local minimum. Now, the idea here is that we can look at our parameters from a physical perspective, and you can see here that when we calculate the gradient, so the gradient here, you can see the minus nabla u. So we take a look at the gradient of the potential energy, and this is equivalent to the force that is applied on the particle. Now, note that the force is related to the gradient, which is our loss function, and the force that is felt by the particle is precisely the negative gradient of the loss function. Now, from Newtonian physics, we know that the force equals m multiplied by a, where m is mass and a is the acceleration. So in this view, the gradient is proportional to the acceleration of the particle. Now, if we go back to gradient descent, then gradient descent takes small steps each time. That means that the steps affect the final position of our parameters. Now, in this view, we actually take a look, we actually see that it is proportional to the acceleration. So the physics view suggests an update in which the gradient only directly influences the velocity, which in turn has an effect on the position. So basically it means that we need to modify our gradient descent update such that we take this idea into consideration. Now, what does this mean? So when we go down the hill, right, then we accumulate speed or velocity, right? So basically, as when we go down, we accelerate. Now, when we reach the bottom, ideally we would want to stop. However, if we don't dampen the speed, then we will just go back right up again, right? So we will just bounce right up and we won't get to the optimum and we miss it. So basically the idea of momentum, what we are going to discuss in a minute, means that we should take into consideration the idea of acceleration. So when we go down the hill, we want to accumulate velocity and go faster in the promising directions. However, we don't want it to accumulate accumulate velocity infinitely. We want to stop we want to stop when we get to the optimum. So the idea is that we need to dampen the speed. So this is the idea of momentum, and let's see how it is formalized. So let's go back to the notebook, and the idea of momentum is as follows. So we have now an additional parameter. We are going to call it z, which is an intermediate variable. And the idea is that we are going to modify the gradient descent a little bit. And you can see here that we are going to initialize this variable z with zeros. And we are going to modify the gradient update by considering this z. So the idea is to introduce a short-term memory. And this memory will help us accumulate velocity, and it will also help us to stop when we reach as the training goes on. So let's take a look. So the momentum is formalized as follows. So zk plus 1, k is the time. Then zk plus 1 equals beta multiplied by zk from the previous iteration. This is going to be our memory. Minus alpha, the learning rate, multiplied by the gradient of our parameters. So here the gradient is the same as we saw before. And when beta is 0, beta is going to be called the momentum parameter. Then we recover the original gradient descent, right? So if you set this zk plus 1 to be just the gradient, this happens when beta is 0, then we just recover the original gradient descent. Now for other values, so let's take a look. So for beta, which is okay, maybe let's take a look at the board. So here's our momentum. So when beta equals 0, then we said it's just the original gradient descent. When beta is larger than 1, then what's going to happen is if we open this recursive term here, we are going to end up with a term which is something like beta to the power of k, where k is the number of iterations. So when beta is greater than 1, then this term will continue growing. So so this term will keep increasing until it diverges. So this will lead us to diverge. Now we want to slowly converge into the optimum. So we want our speed to be dampened when we reach this minimum here. So basically this is what we would like. So we want beta to be between 0 and 1. So this will be our converge parameters, values. So let's take a look. So typically the values of beta are going to be closer to 1. So 0.99 or sometimes 999. And this helps us get the boost that we need to increase our velocity or our convergence speed to the promising directions. Now, our iterations are going to regain that speed and boldness, and they lost, and speeding to the optimum with some energy from the previous iteration. Now, effectively, when beta is between 0 and 1, it dumps the velocity and reduces the kinetic energy of the system. Otherwise, as we just saw, when beta is greater than 1, then we will never stop at the bottom of the hill. We will just jump right back up. Now, let's take a look at some illustration. So W or theta are in the current iteration. Now, remember that we have some velocity from the previous iteration. So beta zt will take us here. So it will take us to this direction. However, when we calculate the gradient, it points us here, right? So this is where we would like to, so this is the gradient. So this is hopefully where we want to end up. However, since we calculate the gradient here, so if you recall, then our update takes into consideration the speed from the memory from the previous iteration and our gradient. So we have these two directions. Sometimes they intersect and sometimes they go different directions. So our final update will be somewhere in between. So we'll be somewhere here. And this is also illustrated here. Okay, so you can see this nice little drawing here. Now, is this good? This is the question, right? And you can already see a small problem here where we actually don't get where we want to be, where the gradient points, but something in between our velocity and our previous our energy from the previous iteration and the current gradient. So we go somewhere in between. So this is not maybe ideal, but we will see how we can fix it in a minute. Now we can see what happens in practice. So we have this nice little demo here, and you can see what happens. So at the beginning of the training, then we accumulate speed, velocity due to our momentum. So depending on our initialization point, we will have this fluctuation in the training dynamics, which is because of this momentum term. And you can see that eventually the speed it's dampened, and this fluctuation really decrease, and we slowly convert to the optimal. Now we can take a look at the effect of the value of the momentum, and when we increase it, then then you can see that it will diverge, and as we get very close to 1, and we discussed why this happens, right? And when you decrease it towards 0, you will get something which is very close to gradient descent, and you can see that it's not optimal. It's very slow, and perhaps it's dampened. We need more iterations to get to the optimal. So we want something which is close to 1, but not exactly 1. So this looks like an optimal value. Now this is a very simple example. Usually beta is around 0.99. Or 0.9, which are the default values also in PyTorch. And this is what we are going to work with. Now, note that momentum usually works in larger batches, and it may break in smaller batches. Now, why does this happen? So, since we are going to change direction a lot because of our momentum, of our energy from the previous iteration, then we can have this, we are going to see these fluctuations in the gradient. Now, when we work with smaller batch sizes, then sometimes the momentum can throw us like really fast in unwanted directions, especially if we have some, for example, outliers in our data. So this is why momentum works better with larger batches. And we will see as we near the end of the tutorial, we will see new optimizers that actually can help us with stabilizing these fluctuations. Now, we talked that maybe this is not ideal. The idea that we are going somewhere in between the actual direction we want to go to. We want to go to. So here is a way to rectify it. So it's called Nesterov momentum, and it is slightly different version of the momentum update. And this is usually what people use nowadays. And why? So it enjoys a stronger theoretical convergence guarantees for convergent functions, of course. And in practice, it works better and it's more stable. Now, the core idea is exactly this one. So if you take a look at here, then you can see that if you take a look here, you can see that this is we ideally want to reach this point, the point where the gradient points to. So the gradient points towards the local optimum, right? And this is the direction we want to go to. So Nesterov is proposing something which is very clever, and it's called the look ahead update. The idea is that we know that the gradient always points to our local optimum. And we also know that we have some energy from the previous iteration. So let's take a look. So we are here. Now we have the energy from the previous iteration, right? So this is a beta ZT, sorry. And it's going to take us here. Now, why not? Since we know we are going to be here, this is our memory. So we also we know what it is. So we know where we are going to be. If we use this memory, we know what is the direction we are going to go. Now, the idea of Nesterov is, instead of calculating the gradient here, calculate it right here. And we know when we calculate the gradient that it always points to the local optimum. So the idea is that if the optimum is here, then when we calculate the gradient here instead of a WT, then we will always go in the right direction, right? So this is why it's called the look-ahead. So instead of calculating the gradient at WT, we are going to calculate the gradient at WT plus our energy from the previous iteration, because we know the momentum is going to take us there. So we'll just calculate the gradient right here, and we know it will take us in the correct direction. So the little fix here is that instead of calculating gradient in WK, we are going to calculate it at WK plus beta ZK, and this is called a look-ahead update. And it's very clever and works really good. And it's a very small fix, which instead of going somewhere in between, we go to the in the right direction. Okay. Now I want to also give some example from real life. So usually when we want to, for example, when we drive, right? So let's consider Formula 1 drivers. So normal drivers, when they have this road here in white, then they will go something like this. Now, Formula 1 drivers, they don't care about the rules. The rules of normal driving. They just want to maintain as much speed as they can. So what they are going to do, they are going to memorize the driving course, right? And they know where there are turns, so they will position themselves such that they lose they don't lose speed or lose very low velocity. So here is the idea. So if we are here and this race driver knows that there are going to be turns, then it's going to make these turns like this. Now you can see that the blue course on the racing track loses much less speed, right? Because turns are causing us to lose speed, and when we position ourselves such that we know where are the turns, then we can position ourselves such that we lose as less speed as we can. Now, this is the idea of look-ahead, right? Because if the driver looks ahead and knows what turns are going to be on the track, then they can position themselves such that they lose less velocity as possible. So this is the idea of look-ahead, and when we do this update here, we don't lose speed because we don't go in the middle, we go in the actually right direction, right? So this is the direction of the gradient, the direction of the optimum. Okay, so I hope it's clear. Now, this is the drawing from before. And what we are going to do now is do some proper examples, code example. And at this point, you should not be familiar with PyTorch, but we know that some of you saw this in previous courses, so let's just pretend that you know some very basic stuff. But we want to introduce the training skeleton already, so it's not unfamiliar in the next lessons. So don't worry, we will see this example over and over again. But it's a good point to it's also a good point to introduce it. So the idea here is to introduce two main things. First, how we initialize an optimizer, and second, how we use a learning rate scheduler. Okay, so our skeleton goes like this. So first, of course, we need the data. Okay, so we are going to load the data. Here we load the MNIST dataset, the digits datasets, the handwritten digits dataset. And datasets just locate the point, the route where the data is located on the disk. Okay, and we optionally can apply some transformations on the dataset. So, for example, all the pre-processing stuff we did. So, for example, we can apply a scaling transform, or as we will see later in the course, there are also some image transformation we can apply. The second thing we do is we take this dataset and we input it to a data loader. Now, what data loader is doing is helping us separate the data to batch sizes, which is nice. Okay, so we don't need to write it manually. And also helps us shuffle the data. So we can tell it to shuffle the data so it's unordered. So as we talked in the recap lessons, shuffling the data is also important. And so we add some randomness to our training. So the training won't rely on the order of the data. And as we'll see in the future, it also helps us use multi-core CPUs, so we can parallelize the data loading to make it faster. So this is why we have these two creatures, the dataset creature and the data loader creature. So they are different. Okay. Next, we define our model. So basically, this is very simple linear model. Two-layer model. We don't know what neural networks are at this point, so let's just ignore it for now. But as you saw in the recap tutorial, then all the neural networks in PyTorch, they inherit from the nn.module class. Okay. Next thing, we define some hyperparameters, and these are some hyperparameters. For example, the size of the hidden layer. And another important thing is defining our device. So our device is going to be very crucial in training neural networks. So basically, we would like to train on GPUs, so CUDA devices for NVIDIA, or MPS for Apple, M1 or M2, and otherwise run on the CPU. So in each training code, we will have the definition of the device at the top of our code. And the idea here is that the device is selected automatically. So when we want to give our code to our friend and our friend doesn't have a GPU, then the device will be automatically defined as a CPU, and the rest of the code will run the same. Okay, so this is why we do this at the top of our code. So now each time we want to transfer data to our device, then we just write to device. And we don't need to think about whether the device is CPU or GPU because it already was defined at the beginning. Now, if you did not use this and you will just define, for example, that your device is just CUDA and your friend doesn't have a GPU, then this line will cause the code to break because your friend doesn't have a GPU, and here you just instructed your code to send your model to the GPU where it is non-existent. So basically the code will fail. This is why you want to do this automatically. So this is why you want this line at the top of your code. The next thing is to define our loss function. So here we are going to do multi-class classification. So as we discussed in the recap tutorial, this fits the framework of cross entropy. More hyperparameters, and now we are going to talk about what is relevant to this tutorial. So the learning rate. And then we define our optimizers. So all the optimizers in PyTorch, all the ones we are going to see in a bit, are sitting under the optim sublibrary. So basically here we call for SGD. And the first thing we do is give it the weights, the parameters of the model. So as we discussed in our recap tutorials, then all the models that inherit from nn.module have this line. And basically this line just gives the optimizer all the trainable parameters, all the trainable weights. The second thing is the learning rate, of course. Now for SGD, we also define a momentum and whether to use Nesterov. So Nesterov is the default one, and momentum, if you set it to 0, then you just get SGD without momentum. Okay. The next thing we do is initialize our scheduler. Now, this is super important, and people usually tend to ignore this part, but it's super important. And scheduler, we can help push your performance a bit further. So here we're going to use the reduce on plateau optimizer, but you can use. I encourage you to start with the more simple ones. For example, the multi-step scheduler. Now here we give the scheduler our optimizer. This is always what we are going to do. And in addition, some schedulers have more hyperparameters. And in this example, we are going to give it our mode. So the mode is max. So we are going to maximize the accuracy. We are going to give it a factor, and factor will always be present, so 0.1. So this means once you reach a plateau in the accuracy, so the accuracy plateaus, then you reduce the learning rate by 0.1. So basically you take your learning rate and multiply it by 0.1. Patience means that how you define a plateau. So patience equals 0, that means no way to. So in this case, we're going to work with epochs. And this means that when we move on to the next epoch and there is no improvement in the accuracy, then just decrease the learning rate. So you can set it to 1, 2, or 3, and as many as you want. So this means that if you set it to 2, then it waits 2 epochs before it reduces the learning rate. So if there are 2 epochs where the accuracy is not improved, then we reduce the learning rate. Verbose means that verbose equals true means that it will print to your screen whenever it reduces the learning rate. So you can tell what in which epoch it reduced the learning rate. And here comes our training loop. So as we discussed before, we are going to have the external loop for the epochs and the internal loop for the iterations where we perform gradient updates. And this means that we are going over all the batches. Okay, now when you use data loader, then it will automatically give you the batches, and you don't need to think about whether or not it covers the entire data, because you are guaranteed that it covers the entire data. So our training loop, we are going to be it's going to look very much the same almost always. And the first thing is getting our data and moving it, transferring to our device. So if we are going to use a GPU, then we need to transfer our data from our local disk to our GPU. The next thing we do is we give it to the model. So basically the model, we apply the neural networks or some model over our data, and we get some output. The next thing we do is calculate our loss. And here comes the 3 lines that will always come in this order and always after we calculate the loss. The first thing is cleaning our gradients from the previous iteration. So basically, as we will see in the next lesson, we have the gradients are stored in the memory. So we need to clean it. Otherwise, if we don't clean it, the gradients will accumulate, and we don't want it. We want to clean the gradients. So this is why we're calling optimizer.zeroGrad. This cleans the gradient. You can think of it like flushing the water. And the next thing we do is after we calculate the loss, we need to calculate the gradients. So loss.backward, calculate the gradients and store them in the memory. So this is the point where we calculate the gradients and store them in memory. The next thing we do is we apply the gradients, and this is what we call optimizer.step. So each optimizer is going to have its own update rules. So as SGD or Adan, they have different update rules. So optimizer.step takes this calculated value of the gradient and apply the gradient update to the weights, to the parameters. So these 3 0-grad backward step will always come in this order, and it will always look the same. Okay, optimizer 0-grad, loss backward, optimizer step. Keep that in mind. Now, after we are done with that, we can decide whether or not to calculate some validation metrics. So we always do that, but here it's very critical because we need this validation accuracy to give it to our scheduler. So here, after at the end of each epoch, after we are done going over all of the batches, we calculate the accuracy and we give it to the scheduler. So the scheduler needs to know what is the current accuracy of the in the epoch and whether or not to decrease the learning rate. So basically here we input the accuracy, but in the simple schedulers, for example, multi-step scheduler, then we don't need to input anything. We just take a step, so this parenthesis will be empty, and then the scheduler calculates for itself how many epoch have passed, and depending on the values you give it, the steps you gave it, then it decides whether or not to reduce the learning rate. Okay, cool. So this is a basic skeleton of how the training looks like. And it will repeat itself. We will see it over and over, so don't worry if it's a bit overwhelming at this point. Okay, momentum is nice, and you can think of momentum as a global update of the parameters, but we can maybe do something a bit smarter, and maybe we can adapt the learning rate for each parameter separately. So the idea is that we're going to apply adaptive learning rate, and by adaptive we are going to mean adaptive for each parameter. So you have 10 features. For each feature we are going to have a different learning rate, which is adapted through the training differently. So how is this going to work, and why it is a smart idea? So here we are going to see that, first of all, it works. Empirically, it works very good. Now, another thing which I hope you can think about is that when in the recap tutorials we talked a little bit about feature selection, and maybe there are features that are more important for our current objective and features that are less important, and this is why we needed scaling. So we don't want to scale to affect our training by meaning that the larger scale means more important features. We don't want that, so this is why we do scaling. But after the scaling, there are still there are still features that are more important than others. And for example, in linear regression, there is a weight for each feature, and there can be some features that are more important. So for example, to determine the weight of a person, maybe the height is more important than the gender, just for example. Okay, so we want to adapt the learning rate such that we go in the direction of the features that give us the most performance. Okay. So we are going to talk about several adaptive optimizers, and all of them are sitting under the torch.optimal library, the same one that we brought imported SGD from. And let's talk about the first one, which is Adagrad. And Adagrad is one of the first adaptive learning rate algorithms with the basic idea of adapting performing smaller updates for parameters which are associated with frequently occurring features, and larger updates for parameters which are less frequent or sparse. Okay, so this is why Adagrad worked really well for sparse data, but it also works for non-sparse data, which is nice. So let's formalize this. So we have alpha, the learning rate, also eta in the lectures. We define the gradient gk, which is the gradient at time step k, and gik to be the partial derivative with respect to parameter wi at time step k. So gik means that we are looking at the ith feature at time step k. So basically we are going to look at each feature separately. So this is why we are going to discuss adaptive learning rate. And we are going to also define a diagonal matrix gk, which is d by d. D is the number of weights. Okay. Now the diagonal matrix is going to have the sum of squares of gradient up to time step k. So this matrix is going to be updated as we continue our training, and it doesn't have to be stored as a matrix, right? Because it's a diagonal matrix, and we only care about the diagonal, so it can also be a vector. But for clarity, let's stick with matrix for now. Now the idea is that we are going to use the sum of gradients as scaling for our learning rate. So here is the Adagrad update rule. So at time step k plus 1, we want, so there is no momentum, okay? So forget momentum for a couple of minutes, and we are just going to look at the original learning rate and gradient update. So we have our learning rate, and you can see that for each parameter, there is a different learning rate because we scale the learning rate by the sum of square gradient, okay? Take the square root here. Now, what happens here? So, for frequent features, the gradient will grow larger at each iteration. So, when the gradients, the accumulation of gradients grows, then effectively the learning rate goes down. And this is what we want. We said that we want to conveniently converge to find the just right learning rate and decrease the learning rate as training progresses. Now, you can see here that this is effectively what happens. And for features or directions which are sparse and the gradient is very low, you can see that the decrease in the learning rate will be slower as well, because this term here will grow much slower. This in contrast, of course, to frequent features. So basically, each feature gets its own learning rate, and we can also formalize this in matrix vector form. It's not important. The idea is that each parameter gets its own learning rate. Okay, so as I've said, notice that there is no momentum here, and we will see in a minute how momentum joins the party. But for now, just let's see how we can adapt the learning rate for each parameter separately. Okay. Now, Adagrad effectively eliminates or alleviates the need to manually tune the learning rate, which is nice, but it's not always true. As we will see in practice, we are going to use a learning rate scheduler with the adaptive learning rate algorithm. So basically, we can combine them both. Okay. Now, so the default learning rate is 0.01, so it's a bit different from SGD. So when you switch your optimizer, then you also need to retune your hyperparameters, especially the learning rate. Now, the main weakness is the accumulation here in the denominator. The problem with that is that it keeps growing during training and causes the learning rate to shrink, right? The learning rate will go to 0 very quickly, usually. Now, at this point, the training is stuck, because when the learning rate is effectively 0, we don't take steps anywhere, and basically you will get a plateau, which is because of the learning rate is 0. Now, the problem here is that there is no smoothing term for this gradient accumulation. So this term here in the denominator grows very large, very fast. So after a couple of iterations, the learning rate will just be 0. So how we can fix that? Now, you can call Adagrad for research purposes in PyTorch. It's not what people use today usually, but if you have some idea how to modify it to make it better, then you can still use it. Okay, now how can we fix that? And a couple of years later came an algorithm called RMSprop. Now, there is a very interesting story about RMS, and which is unlike everything else that we are teaching you. So 99% of the things we are teaching you are based on academic papers. Now, this one algorithm, which is very popular, is proposed by Jeffrey Hinton, which is one of the pioneers of deep learning. But there is no academic paper about it. Jeffrey Hinton introduced it in a presentation teaching slides for his course. And you can see the slide right here. And the funny thing is that when people use RMSprop in their academic projects, and they write a paper and they need to cite RMSprop, they just cite a slide from a lecture, which is very funny because we don't do that usually. Okay, so what RMSprop proposes is to fix Adagrad by doing a moving average of the accumulation. So instead of just adding the gradients infinitely, basically what we can do is smooth this accumulation by using something called the moving average. And the idea is very simple. And this idea, we will see it a lot in this course. And we will call it sometimes EMA, which stands for exponential moving average. And the idea of EMA is that we don't take big updates. We do it slowly, and this is how it's going to go. So we are going to define GK, and we are going to define with E of G squared the moving average of squared gradients. So this is like expectancy, but not really, okay? Now it's going to be stored in our memory, and this maybe brings you some flashes of momentum, but we will see how it integrates in this idea as well in a minute. So RMS proposes to fix Adagrad by, instead of using proper, or I don't know, maybe non-smooth accumulation, we're going to smooth the accumulation by the following update rule. So this denominator here, which is going to be the square root of the squared gradients, is replaced with a moving average of the squared gradients. And the idea is that we are going to have this moving average parameter beta, and it's usually 0.9. And basically we are going to take our memory from the previous iteration of the moving average of our gradients, and then we just add very small portions of the squared gradients in this iteration. So basically we will get a very smooth version of this accumulation. Now, why is this justified? So the learning rate is adapted by dividing the root of the squared gradients, but since we only have the estimate of the gradient on the current mini batch, so we recall that we are doing mini batch gradient descent, then we instead use the moving average of it, and this smooth this accumulation very much, and the decrease to 0 will be much slower. So this idea, which is called EMA, is going to come back a lot later in the course, and just so EMA, we will see it in the tutorials later, but for now the idea is as follows. So let's say you want to find some to update some parameters, and then the final update to these parameters will be some a moving average of this parameter. So basically we're going to have some memory of the moving average, and beta is going to be something like 0.9 or 0.99, and then we calculate some value from our current iteration, but we don't use the entire of it. We just take a little portion of it and add it to the moving average. So this smooth and stabilizes the training process a lot in many applications. We see it here for the learning rate, we will see it later for the parameters, and we will see it also in self-supervised learning. So there is more to come from this idea, so keep that in mind. So RMSprop is quite popular, but again, there is no momentum here, right? We talked about scaling the learning rate. So how we can add everything together. So this is why Adan, the very popular, the king of optimizer, came into play. And Adan is going to combine the idea of EMA, the moving average, of the scaling of RMSprop and Adagrad, and the momentum, okay? And this is how we are going to do it. So Adan is going to introduce two separate quantities. We are going to have the squared gradients. The moving average of the squared gradient is going to be called V. This is the same one from RMSprop, and this is going to be updated as follows. We are going to have beta 2, but for the gradient itself, so we want to use some ideas from momentum. So instead of the gradient itself, we are going to use a momentum, a moving average of the gradients. And the reason why I'm saying that it is a combination of momentum and the idea of EMA is because if you take a look at the gradient itself we are going to use, which is the moving average of the gradients, then you can see that it's very similar to the idea of momentum where we have beta. However, it's a bit different because we have beta 1 and 1 minus beta 1. So beta 1 is sort of the momentum, but it's going to be considered also in the gradient update. So if we jump just a little quickly here to momentum, you can see that we have beta on the memory, but we don't have 1 minus beta on the update. And here we take beta here and multiply it by our memory of the gradients, and then take the 1 minus beta 1 multiplied by the current gradient. So basically we have all of these ideas. So it takes up more memory, and beta 1 is usually like the momentum value 0.9, and beta 2 is usually something 0.99, and the update is going to look something like this. I'll just know that since we are going to do some statistical estimation of the gradients and the squared gradients, the moments actually, then we want to take some unbiased estimation. So if you're familiar with statistics, then we want an unbiased update. So we do a little fix here to the updates. So it's just technical. So the update then is going to be alpha, the learning rate, scaled by the moving average of the squared gradients, and multiplied by the moving average of the gradient. Okay, cool, very cool. And just note that we have a smoothing term here, epsilon, which is super important and people tend to neglect it, but it's default to 10 minus 8, but it's not usually a good default parameter, and you should tune it as well. So you should start with, you should also look for values in the range of 1e minus 3 and 1e minus 12 as well. So you can see some recommended articles. So epsilon can really affect the training dynamics, and sometimes setting it to higher values, so something like 1e minus 4, can lead to a more stable training dynamics depending on your task you are optimizing for. So Adam is the king of optimizer, and this is what we're going to usually use, and you can see it here. So basically we have more hyperparameters to tune. So we have beta, and we also have epsilon. And basically, if you want to apply Adam with weight decay, L2 regularization on the weights, then there is AdaW. And the reason we have two different optimizers is because in the original Adam paper, they did not take into account the L2 regularization, so the update is implemented differently. So basically, if you want to use weight decay or L2 regularization, then use AdaW. Now there are many variants of Adam. You will see there's AdaW, AdamN, and Nadam. There are many optimizers. So you will see that usually you can start with Adam, and then you can look for other improvements. So how do these methods compare to one another? So we have this nice little animation here. We can take a look. So there are a couple of things to notice here. Okay, the first thing is that SGD, which is the red curve, it's quite slow, and we understood in this tutorial why. And then we can take a look at the momentum one. So momentum and Nesterov. So we can see the Nesterov is more well behaved, but both have this overshooting behavior. So this is because of this unbounded and very unscaled, let's call it like that, momentum update. So now if you take a look at the adaptive one, so Adagrad, RMSprop, and Adam, you can see that the moving average really stabilizes things, and maybe a bit slower than momentum, but they're still nicely converged to the minimum. So this is why people prefer to use them today. However, I'll just note that SGD is still widely used in many applications, and usually on very popular tasks when you want to report your performance on some benchmark, you usually keep to the same recipe, which is using SGD as your optimizer. So don't neglect it. Okay. Now another comparison is when we are getting stuck on a saddle point. Now you can see that unlike the momentum-based optimizers, the adaptive ones, they can escape the local minima, and this is because if we'll take a look, for example, at RMSprop, unlike SGD, it can break the symmetry because each parameter, each feature, or each direction is optimized as a different learning rate. So basically, the idea is that if we change the learning rate for each parameter separately, then we can escape local minima by taking larger steps in directions that are in different directions. Now, RMSprop. So what happens here is that we see very low gradients in the saddle directions. So these are features, okay. And due to the denominator term in the RMSprop update, we can actually increase or have a larger learning rate in the promising directions, which help us escape the local minima. So this is nice, and this is why it's very helpful to use the adaptive learning rate. And basically, this is what people do today. So there is a saying that the community, the machine learning community, is overfitted to Adam. So everybody uses the Adam optimizer and without considering other optimizers at all, which means that the optimizer is no longer a hyperparameter, but it is. So our Adam works so good, so basically people don't think about changing it. So let me try tell you about new optimizers. and hopefully you can try them and see if they work better for you. So Adam is the king of optimizer. It has been the go-to optimizer for some time now. And while there were several attempts to dethrone Adam, there was not a major breakthrough in the optimizer literature, and Adam is still the one people use the most. However, there are several notable recent works that propose the alternative, and they show great candidates to replace Adam, but they are new and they are not that widely used, so they are not implemented in the PyTorch library yet, but they are available in PyTorch, like an external code, so you can download the code and use it as well, but it's not under the torch.optim library. So the first one is AdaBelief, and the motivation is to achieve 3 goals: fast convergence, good generalization, and training stability. And they are going to modify the Adam optimizer just a bit. So you remember that the second moment update, then we are going to modify it just a little bit by considering the delta between the difference between the gradient and the prediction of this gradient, which is going to be called AdaBelief, and it can be, so it's calculated the same way as we calculated it in Adam, but basically we just instead of using the squared gradient, we are going to use our delta in belief. Now, AdaBelief was introduced in 2020, and it showed real promise in many problems, and it showed that it converges faster than Adam, but it has not become very popular. But I encourage you to try it. There is a PyTorch code here. You can try it out and see if it works well for your applications. Another one, which is quite recent, is called MADGRAD. It's by Meta, and MADGRAD is going to build upon Adagrad, and here is the idea is to combine the original momentum with some modifications to improve Adagrad, and the idea is we want to achieve the generalization performance of SGD with the fast convergence of Adam. And you can see the update here. It's not that complicated, and there is an open code, but there are a couple of caveats. First, it works only on GPU. And it's different in the way we are used to work, by that it requires different tuning than Adam. So you should not transfer your Adam hyperparameters to MADGRAD without doing some retuning. Okay, and the last one, which is the most recent one as well, is called Adan with an N. And Adan is quite recent, is also from 2022, and the idea is to use a new Nesterov momentum estimation. And the idea is that we can improve the training speed and stability, and the algorithm here, it's very similar to Adam and to AdaBelief. The idea is that we are going to use, also we're going to have beta 1 and beta 2, but we also have beta 3. So beta 3 is going to be part of the new Nesterov momentum estimation, and you can see the update rule right here. So basically it requires tuning another hyperparameter, which is beta 3, and basically the algorithm is quite straightforward with the calculations. And there is for all these algorithms, there is theory and convergence guarantees for convex functions. You can see it in the original papers, but for practical approaches, you can see that it's not that all of these algorithms are going to be based on a moving average and some estimation of the gradients in one way or another. Okay. Now Adan shows better performance on Adam, but it's on these popular benchmarks, and it's not. So when you have a new loss function, a new task, then usually you just try things out, and some optimizer might work better than others, but for the popular benchmarks, then it seems that Adan, the new one, it works quite well, especially over Adam, which is the king of optimizer. Now, just one note, it should not affect you in small applications, okay? You're not going to train the next language model with your academic budget probably, but just note that Adan is a slightly higher GPU memory course than Adam and Adam because we need to also have the moving average of the third term here, the NK, in addition to M and V. Now, there are recommended videos here. Again, there are no new videos on MADGRAD and Adan yet, but maybe they will, so keep an eye on that. And that's it for this tutorial. Thank you for watching, and we will see you next time.